So in the previous lecture, we talked about standard linear models, and we have data, a model for our example here, our example of extremely tight linear regression coming from the Nieder et al. Statistics book, where you have y, the data, equals b0 times 1 times plus b1 times the x data plus an error term. And what we showed is that you can, in a linear model, you can do a fit based on minimizing the residual sum squares. And when you do this linear model, minimizing the residual sum squares, you get coefficients for the b0 and b1 such that the sum of the squares is minimized. And this gives a very, very tight regression line. And we can conceptually think about this. Right? This is the line. The guarantee is that the data points, the square of the distances to the data points to this regression line on average will be smaller, or there's no line that you can draw that's a better fit. So there's no line that's going to make these data points come closer to the line, where again the distance is measured as the sum of the residual sum squared. So this is here we use column vectors, but in fact we can use a more concise notation, and that will lead us to solve both more complex linear models that have more parameters than just the two that are shown in the simple linear regression. And will also allow us to use an alternative algebra based on taking a derivative of the matrix of this equation instead of each of the individual column vectors. So we can ask R to save the matrices that it's using and allow us to inspect these matrices by setting this x equals true in the linear model. So here I have my linear model of my y squiggle x the way I make any linear model, but I set x equal to true here. And then when I say x equal to true, I get the data matrices that are used, right? So these are the column vectors, the two column vectors put together in a single matrix, and we will recognize the column vector as being the intercept vector, right? So it's this vector here, and the x data vector as well, right? And so we can put this together, right? We can express our equation y equals b0 plus b1 x plus e by using these notations, right? So I have my y data, the matrix of the column vectors joined together into a 10 by 2 matrix here. The coefficients are 10 and 2, that's b0 and b1. These are the residuals, right? So these residuals here represent the error terms. So I can kind of solve for the y data this way, right? So y equals b0, so that equals this coefficient, the intercept, times the identity vector, so I don't need to put that into my R, although I can if I want to, right? So I can say b0 times the identity vector, that's the identity vector, the first column of my matrix here, plus b1, right, and that's the second coefficient that I get from the linear model, times the x data, which is stored as the second column of this 10 by 2 matrix, plus the residuals, right? And so when I do all of that, I get my data back. Right? So I'm just using all of the R. R is allowing us to get all of the pieces of the fit by typing all of this in here. But if we make this more concise, we can generate a way of solving for these variables that will extend to any number of variables, not just the two parameters of a standard regression model. And here for the first time, I'm going to be taking a few pages from the Elements of Statistical Learning, a very, very, very excellent machine learning textbook. And like many machine learning textbooks, this textbook starts with basic linear models, because linear models are the building blocks of more complex and more sophisticated machine learning algorithms. Right? So we can express this equation again by having the intercept be this column vector of ones. We can express this equation very very succinctly as the y hat, right? So that's everything except the errors, equals the transpose of our data, which the first column of this would be ones transposed, right? This transposed, and the second column would be this transposed. So we transpose this and multiply it by our b0 and b1 coefficients, and that will give us the model, right? And now what we know is that similar to the algebra that we worked through with just two parameters, we can now work through the same algebra where we express now our error as being, right, if this is our model from this equation, this is our error squared, so we recognize this is the sum squared errors, and we do the same trick of taking the partial derivative of this thing, setting it to 0, and then we can solve. So if you grind through this math here, you can solve directly for the beta parameters with this equation. And sometimes I call this, my daughter is going through Lord of the Rings right now, so this is one equation to rule them all. So this is going to solve, this is going to be a linearly square fit for any linear model, no matter how complex the linear model is, no matter how many variables you have. So maybe you have variables for BMI and hospital and gender and age, and it's all stuffed into one giant linear model. This will give you the least linear squares fit, no matter how many columns you have, how many columns of data that you have here. And this can simplify our code to get the coefficients in R, right? So here's my Y data, here's my X data. So if I say X as matrix C bind rep 110X, and so here I just have my design matrix, or my matrix with the data, with the intercept and the X data. I take the transpose of this thing, right, and that just transposes the rows for the columns, right? And here's my one equation to rule them all. So I just put this into R. I solve this for the inverse of this of the transpose of this matrix times itself, and then just do carry through matrix multiplication. These are the symbols for matrix multiplication in R, and out pops a 2x1 matrix with my parameters. So this is the least, again, these are the parameters that guarantee that the residual sum squares is minimized, and this residual sum squares is minimized. In this case, this is redundant to the algebra that we did for simple linear regression, but because this is in this notation, we can expand this to any number of variables. We can use the same equation, right? So with very little typing, I can recover the 10 and the 2, which are the correct parameters here. And of course, this matches up with what you get in R when you type summary linear model y squared equal x, and it matches up with the derivatives that we took for the simple linear regression in the previous lecture. So we're next going to review from your first semester stats class the ANOVA approach to linear regression, and also show that the ANOVA approach will also generate an equivalent to the t-test with equal variance. And this is reflecting the fact that the ANOVA approach is just incredibly flexible. So you can give it any linear model, and it can generate p-values for you because it has a consistent set of algebra, and in which you always compare a more complicated model to a least complicated model. So if you can just define which two models you want to compare, a more complicated and a less complicated model, the ANOVA can generate a p-value that the amount of variance that is captured between these two models is significantly different. That is to say, the null hypothesis will be that the two models are as good at describing the data, and you can reject that null hypothesis and say that the parameters that make up the more complex model are significantly different because when you take those parameters away from a simpler model, you capture a significantly increased amount of variance. So that's a mouthful to say and a mouthful to understand. And so to start to break that down, we're going to define the F distribution, which is, I think, might be the last distribution we're going to do this semester. So the F distribution is going to be used to test for testing statistical significance from these ANOVA models. And the F distribution is defined as the ratio of two chi-square distributions divided by their degrees of freedom. So like the chi-square distribution and like the t distribution, the F distribution is a distribution that's based on standard normal distributions, right? So the U1 and U2 here are both chi-square distributions with sample sizes of D1 and D2, so with D1 and D2 degrees of freedom. And the F distribution is simply the ratio of these two chi-square distributions divided by their respective degrees of freedom. And so it's based on the chi-square distribution. You just sample the chi-square distribution, do it twice for two different degrees of freedom, take the ratio, and you have the F distribution. As usual, and I think this is, again, maybe the last time we're going to do this semester, we have DF, PF, QF, and RF. So really, I think this is for the last time now. The probability density function of the F function, the cumulative distribution function of the f function, the inverse cumulative distribution function, and randomly sampling from the f function. Notice the f function has two parameters, the number of degrees of freedom in the numerator and the number of degrees of freedom in the denominator. We're going to be using the f statistic for our to evaluate statistical significance of the analysis of variance, and these 2 degrees of freedoms are going to relate to the two models, to the number, the sample size in the models, and to the differences in the sample size between the models, as we'll see shortly. As usual, we'll go through and we'll just make this demonstrate that our understanding of the f distribution is correct. So here I'm just going to calculate kind of a homemade f distribution. So I'm going to say I have f values that I calculate manually by taking a chi-square distribution, by taking one chi-square distribution and dividing it by its degrees of freedom, taking another chi-square distribution, dividing it by its degrees of freedom. My homemade f values are just here in f values 1, top versus bottom. The ones built into R are going to be random sampling from the top degrees of freedom and bottom degrees of freedom. I have a large sample size. I do a QQ plot, and what you can see is that that these values are almost exactly the same. So my expected distributions under one look at the f function is the same as my expected distributions under second look at the f function. So that gives us some confidence that our understanding of what R is doing for the f distribution is correct. So with the f distribution, which we're going to use for inference defined, we can take a look at the ANOVA approach to linear regression. And it might seem a little, this is going to be a little redundant because we're going to end up with the same p-value that we got for the matrix form of linear regression. But it's not always going to be true that the ANOVA approach to linear regression is going to give you the exact same p-value as the matrix form of linear regression. It is, however, true for the simple linear model that you get exactly the same answer. So the ANOVA form of regression is based on calculating errors of different models and comparing those errors to each other. And so we have to think about the kinds of errors that you can calculate in linear regression. And then we'll use the ANOVA approach to analyze these variances, right? So it's called analysis of variance because you have these different kinds of variance, and you're going to compare the variance from the different models and then decide whether the parameters that you add from a particular model statistically reduce the amount of variance in that model. That is to say, when you compare two models, do you get a statistically significant reduction in the error that justifies the addition of additional parameters in a more complex model? So that's pretty abstract, but to make this a little bit more concrete, let's start to go through and think about the kinds of errors that you can generate in a linear regression model. So this first one is familiar because it's related to the variance of the model. In fact, we recognize this as being the numerator in our definition of variance, right? If I just divide this by n or n minus 1, I would have a sampler population variance. Right? So this is yi, every data point, minus y average. Right? So in the Nieder book from which this figure is taken, this is called total sum of squares. Right? So you have the y average, right? And then you take yi, and then you look at all the data points, and then you sum up the squares between y and y average. Now, we're not used to thinking of the average as being a statistical model, but in the ANOVA vocabulary, it is a statistical model. It turns out it's going to be a model with one parameter, right? So you have all of your data, and you have one parameter, which is the average, right? And then we can ask how well does this model fit the data, and that's going to be the total sum of squares, so yi minus y average, right? We can add a second parameter, right? If you go from a simple, this is going to be a simpler model in the ANOVA world that has only the average. This is a line, right? So notice the data points haven't changed here. These are the same data points. But now with the second parameter, you have not just a mean, but you have a slope and an intercept, right? So the average only can have can only be in one dimensional and only has one parameter, right? But this line has both a slope and an intercept, right? And so we're going to be able to capture the data better with two parameters versus one parameter. What the ANOVA test is going to assay is how much of the data do we capture with the second parameter versus the first parameter, and is that a statistically significant difference? So we're going to be evaluating that with the f distribution. So what's the error associated with a linear model? Well, of course, we know that. That's the residuals that we just defined in the previous lecture. Right? So this is the sum of yi minus y hat squared. Right, so we have, right, just like we have had in the previous lecture, here are all of our data points. Here's the regression line. The regression line is y hat, right? The regression line is y hat. right? So that's the regression line here, right? And yi is each one of the individual data points, right? So the residuals, just like we saw before, is the sum of yi minus y hat squared, what the model doesn't capture, right? So this is a 2-parameter model. yi minus y hat squared is what is the variance the 2-parameter model doesn't capture. This is a 1-parameter model. yi minus y average square is the variance that the 1-parameter model doesn't capture. And now we can think about this total sum squared, actually, right? If we subtract off, if we take the total sum squared minus the sum squared error, what we get is this regression sum squared. Or another way of saying that is that the total sum squared can be decomposed into the sum squared error and this regression sum squared. So we're going to define the regression sum squared as y hat minus y average. And that's sort of an odd thing to think about. It's the difference between the regression line and the average, right? And this is going to tell us something about the significance of the model, because remember, when we test a null hypothesis, it's at the slope equals 0, right? And so if the slope equals 0, right, then this model is perfectly fine. If the slope doesn't equal 0, then the regression line will lift off of this average model, right? So this total sum squares is decomposed in an ANOVA analysis into the sum squared error plus the regression sum squared, right? So if I do yi minus y hat I plus y hat I minus y average, when I add all of these together, they come out to, right, the y hats drop out, right? This is yi minus y hat plus y hat I, right? So these drop out, right? The model line at each point minus y average, and what you're left is yi minus y average squared. So the total sum squared is equal to the sum squared error plus the regression sum squared. And the regression sum squared also seems to be relating to the inference, because if the null hypothesis is true and the slope equals 0, then the regression line is going to be pretty close to the average line, so this number is going to be small. But if the regression sum squared if the slope is really not 0, then this difference is going to be a bigger value because the regression line will be far away from the average line. So we can almost think about the ANOVA test as looking at good variance versus bad variance. This is bad variance, right? This is variance. This is what is not explained by your model, and this is good variance. This is how much of the variance is explained by your model. And the ANOVA is going to allow us to put p-values on these hypotheses, on a null hypothesis that the model isn't explaining very much. So we can calculate all of these very simply in R. We can get the total sum squares by just grinding through. So here I'm just manually grinding through in a for loop, or, right, because this value is, right, if you divide by n minus 1, that's the variance. So if I just take the variance and multiply by n minus 1, I get the total sum squares, right? So the total sum squares, the yi minus y average here is 13,660. This is the variance that we need to partition in our ANOVA model. The sum squared error is our residual sum squares. It's how much does the data differ from the regression line, right? So it's yi minus yi minus y hat I, right? So for each data point, how much does the data differ from the regression line squared? All right, and what we know for this data set where the regression is very tight, as we'll remember from the previous lecture, this is a very, very strong relationship. So this total sum squares is actually very small. These residual sum squares errors are actually very small, right? So because this is a very, very tight correlation, the sum squared error is the data points are all very close to the regression line. So this residual sum squared is very small. And finally, we have the regression sum squared, which we can again calculate as the difference between these two. And if we just grind through these values in R, this is what we get here. So this is looking at the just this equation translated into R, and you can verify that's done correctly, and that's the value that we get here. So again, the question is, how much is good regression versus bad regression? Now, this is a very tight fit that's shown here. So in this very tight fit, where the data are very close to the model, we have mostly the good regression, right? Our model fits the data very well. Our 2-parameter model fits the data very well, so there's not much error associated with the total residual sum squared here is only 60. These data points are not very far from the data line, and because it's a good fit, the regression line is far from the mean line, right? So this number is really high. Now, if we take the ratio of these various values, right? So if we look at the good regression value divided by the total regression, that is a definition of R squared. And you will remember R squared as the correlation coefficient from your previous semester. You can think of it as how much of the data, like if I give you the data on the x-axis, how much of the data do you know on the y-axis? So we say that we know 99.5%, 99.56% of the data on the y-axis given the data on the x-axis. So we can define this R squared this way from thinking about this in terms of the ANOVA perspective. You can get it when you do the summary linear model. R will give you the R squared of 0.9956. Or alternatively, because it's R squared, you can just get the correlation coefficient directly from R. This is going to be the Pearson correlation coefficient. You can say core yx squared, core yx times core yx, and you get the same number. To think about this in terms of inference, right, we have our usual equation y equals b0 plus b1x plus e. We want to know if b1 is significantly different. In the previous lecture, we saw how to do this with the t-distribution, so we worked through the proof that if you take this estimate, right, your linearly squares fit, you get an estimate of 2, and then we had this standard error of that estimate, which we went through the algebra for in the previous semester, and we said the ratio of these two things was t-distributed with n minus 2 degrees of freedom, and you got this p-value of 1.02 times 10 to the minus 10th. So the ANOVA approach takes a different approach. So the ANOVA approach says, well, let's consider this as the full model. What's the error associated with this model? So we know the error associated with this model is just the residual sum squared, right? So the error associated with this model is just the distance of the data points from the regression line, and that's the sum of the residual squared, and that's 60, which we just showed. And furthermore, there's 8 degrees of freedom associated with this model because we have 10 data points, and we have 2 parameters. So this is the full model. Now we have a reduced model. We take away the parameter we're interested in. We're interested in this B1, right? So we say, well, what if this is 0? Our null hypothesis is that this is 0. So let's just make it 0. We now get a reduced model. And this reduced model is the one parameter model. It's this model, right? The only parameter we have is the average. If you have all of these data points, the average is defined as the value which is in between all of these data points, which minimizes the residual sum squares from all of these data points to the average itself. Right? That's how it's not the way we usually think of defining average, but you could define that. It's right. There's no line that you can draw that's going to be closer to all of these points than the average line. That just comes from the definition of the average. So the estimate, the error that's associated with the average is just the sum of yi minus mean y squared, right? So that's our reduced model, y minus y average squared, right? There's 9 degrees associated with this model. So to get a p-value from this, our test statistic, and I would actually have you guys, if there was going to be a final this semester, I would have you guys memorize this. This is always a question on one of my finals. I would give you these various errors and ask you to put this in, but we'll have to find some other way to get this into your brain since there won't be a final this semester. So our test statistic that's going to be F distributed is the reduced error minus the full error. So I just chug these numbers in, minus the difference in the degrees of freedom between the models. So in the numerator here is going to be 13,600. And we normalize that by the full error divided by the full degrees of freedom, where the full error had 60, if you go to the previous slide, divided by 8 degrees of freedom. So you grind through this, and this comes up with this number, 1,813.3. And our p-value can be gotten from a one-sided test saying that this is F distributed, remember the F distribution from just a few slides ago, with degrees of freedom in 1 and 8. Right, 1 corresponding to the numerator of this equation, corresponding to the difference between the complex model and the reduced model, and then we divide that by the error associated with the full model. So we do this, and we get a p-value of 1.0 times 10 to the minus 10th. We can also say ANOVA my linear model to get this p-value of 1.0 times 10 to the minus 10th. And when we do that, the ANOVA gives us these values, right? So the values associated with the reduced, the full, and the degrees of freedom. So the numbers that we're plugging in here, we can get from our ANOVA table here. And of course, this is the same p-value that we get by typing just summary linear model, 1.0 times 2 to the minus 10. When we type summary linear model, the summary function for the linear models actually does this both ways. It gives us the t-test version of this p-value, which is 1.0 times 10 to the minus 10th, and it gives us the F statistic version, which was 1,813 with 1.8 degrees of freedom, PF distributed with a one-sided test, and you get 1.0 times 10 to the minus 10th. Now, again, for simple linear regression, these two numbers will always be the same, but it won't take us very long as we get to more complex models where you'll start to see differences between the p-values for the ANOVA and the regression. Right? So again, we can kind of think of this like we have our reduced model, our full model, right? So the reduced model is the only has the average. The full model has the differences, and then we're looking at the difference between them here. We're using the F statistic to look at the difference between the two models divided by the full model with the appropriate degrees of freedom. And that's how you do an ANOVA approach to linear regression.